In this lecture, we talked about two main non-metric methods, namely decision trees and rule-based. In decision trees, we talked about card C4.5 and ID3. Let's look at an example of a decision tree. Given a training dataset with 10 records and a number of attributes such as refund, marital status, taxable income, and cheat. Cheat is the class which contains the labels of the records. The data then can be used to train a decision tree. In this example decision tree, the attribute refund is considered first. At this node, the training set is split based on the values of the attribute refund. If refund is yes, then the records are labeled as no cheat. Otherwise, the next attribute to be split is marital status. At this node, all the records that reach the node are splitted. Records in which marital status is married are labeled as no cheat. Otherwise, the next attribute, taxable income, is considered. Records with taxable income greater than 80K are labeled yes and otherwise no. This is another example of decision tree with the same training dataset. Now we can see marital status is considered first, and then refund, and then taxable income. So there could be more than one tree that fits the same data. In classification task, the training dataset is used with the algorithm to train a model, and then the model can be used to classify test records. Given a test record with refund, marital status, taxable incomes given, the task is to label the record as cheat or no cheat, starting from the root of the tree with refund. Here refund is no, so the record is sent to the node on the right. Then marital status is considered. And because marital status is married, so the label is classified as no cheat. There are many decision tree algorithms. Hans algorithm is one of the earliest, and then card, ID3, C4.5, as well as Slick and Sprint. In Hans algorithm, let the set of the training records associated with the node and omega j is the class labels. The general procedure is if D contains records that belong to the same class omega j, then N is a leaf node labeled as omega j. If D contains records that belong to more than one class, use an attribute test to split the data into smaller subsets. Each child node is created for each test outcome, and records in D are distributed to the children based on the test outcome, and then recursively apply the procedure to each subset. At each node, the test condition depends on the attribute types as well as the branching factor, or also called branching ratio. This factor is the number of splits. The root node splits the full tuning set, and then each successive decision splits a proper subset of the data. When the branching factor is equal to 2, then it is called two-way split, and otherwise it is called multi-way split. First, we talked about test conditions for nominal attribute. If it is multi-way split, then the number of links B is equal to the distinct values. For example, in the insurance dataset, the attribute account type may contain 3 distinct values: checking, saving, and CD. So the number of links from the node account type is equal to 3. If it is two-way split, meaning the branching factor B is equal to 2, you can combine the distinct values, for example, checking with saving, or saving with CD, or checking with CD. How about the test conditions with ordinal attributes? It is similar, except that the order of attribute values have to be maintained. With continuous attributes, there are different ways of handling either discretization to form an ordinal attribute, or select a value V for two-way split. This slide illustrates the two methods. These are the measures of node impurity, including Gini impurity index used in cart, select, and sprint. Information gained based on the concept of entropy used in ID3, C4.5, and C5.0, and misclassification error. How to find the best split? In general, you will need to measure the impurity before split as well as after the split, and then compute the gain or the reduction of impurity, and from there to decide the best split. Variance impurity is one of the definitions of impurity. In a two-class case, with the desire to have zero impurity when the node has only one class, the impurity at node N is the fraction of records at node N that are in class omega 1 times the fraction of records at node N that are in class omega 2. The generalization of the variance impurity is called Gini impurity, and it is the sum of the product of the fraction of records that are in class omega j times the fraction of records that are in class omega I, with I not equal to j. This Gini impurity can be rewritten into a better form, as you can see. The maximum of the Gini index is 1 minus 1 divided by NC, where NC is the number of classes. This is when the records are equally distributed among all the classes, implying the least interesting information. And the minimum of Gini index is 0. This is when all records belong to one class, implying the most interesting information. Gini index is used in algorithms such as cart, select, and sprint for testing conditions. When the node N is split into B partitions or subsets, the drop in impurity delta I split is equal to the impurity at node N before split minus the sum for all the partitions of pk times the impurity at children nodes nk. And pk is the fraction of churning records sent to the node nk. Now let's see how to use Gini index with binary attribute. Consider the sample insurance dataset with 10 records. The class is by with labels no or yes. The attribute have children is binary. Before the split, in the churning records, there are 5 records in class yes and 5 records in class no. Gini index before the split can be calculated. Records in which half children is no are sent to the left node, and records which have children equal to yes are sent to the node on the right. Among 3 records that are sent to the node on the left, 1 record is in class yes and 2 records are in class no. And similarly, among 7 records that are sent to the node on the right, 4 records are in class yes and 3 records are in class no. From this, you can easily calculate the Gini index after the split at the node on the left and at the node on the right. And from there, calculate the Gini index of the split. The drop is the Gini index before the split minus the Gini index after the split, and that is the drop in impurity. How about Gini index with nominal and ordinal attributes? First, let's consider the splitting factor b greater than 2. Here the number of links are equal to the number of distinct values. Marital status has 3 distinct values, including married, single, and divorced. So records from the original Gini set are split and sent down following 3 links. With the status of married, you have 1 yes and 3 no. With the status of single, you have 1 yes and 2 no. And with the status of divorced, you have 0 yes and 3 no. Now from there, similarly, you follow the same steps to calculate the drop in impurity. You can also do two-way split, in which the splitting factor b is equal to 2. At first, you need to look for the distinct values and then combine them such that you have 2 groups. In this example, you have married and single on the left and divorced on the right. Following the same step, you can calculate the drop in impurity. Another combination of distinct values give you married on the left and divorced and single on the right. And you can also group married with divorced and leave alone single. So among 3 different combinations, you can see that splitting with married and single and divorced is the best among two-way splits. because the subsets are pure. And also, multi-way split is better than two-way split. How about Gini index with continuous attributes? One of the ways is to get all the distinct values and then split the Gini set at each value. For each value, scan the database once to gather the count matrix and compute its Gini index. This method is simple and called brute force, and it is computationally expensive. To be more efficient with each attribute, the first thing to do is to sort the attribute on the values and take the midpoints, then form the count matrices and compute the Gini indexes, and then select the split with the least Gini index. This example shows how we process the credit limits attribute. At first, the values are sorted, and then the midpoints are calculated or computed. With each midpoint, calculate the count matrix. And then compute the Gini index of the node on the left and the node on the right, and do this for every midpoint. And then from there, calculate the Gini index of the split. Select the split with the least Gini index. And here in this example, we have two same Gini indexes. But when you have many more records, then this case is rare. In addition to Gini index, splitting can be based on information gain. The entropy impurity at the node end is defined as in the formula. It measures the homogeneity of a node. The maximum is log of NC when the records are equally distributed among all classes, and this implies the least information. The minimum is 0 when all the records belong to one class, implying the most interesting information. The computations are very similar as with Gini index. Information gain is defined as the impurity at node n, or the entropy at node n, minus the sum for B branches of pk times the entropy at node nk, and pk is the fraction of tuning records sent to node nk, which is nk divided by n, and n is the number of records before split. Information gain measures the reduction in entropy achieved because of the split. Choose a split that achieves the most reduction. Information gain is used in ID 3 and C 4.5. The disadvantage is it tends to prefer split that result in large number of partitions, each being small but pure. In that case, the information gain needs to be scaled by the split entropy, and this results in the gain ratio. Gain ratio overcomes the disadvantage of information gain and is used in C 4.5. The higher the splitting factor, the more penalized the gain ratio. With the same example as we did with Gini index, In the case of binary attributes, entropy before the split and after the split can be calculated, and then the gain and the gain ratio. With the case of nominal and ordinal attributes, when the splitting factor greater than 2, we first need to get the distinct values. The number of branches is equal to the number of distinct values, and then follow the same procedure to calculate the entropy before the split, after the split, and from there calculate the gain and the gain ratio. If you use the splitting factor equal to 2, then you need to see which combinations of distinct values give the best split. So we go through the same process, and then we can see that splitting with merit and single combined and divorced is the best among two-way splits. And another conclusion is multi-way split is better than two-way split using gain. However, if we use gain ratio, then two-way split is better. Information gain with continuous attributes is similar as with Gini index. Instead of calculating the Gini index, you calculate the entropy, gain, and gain ratio. Splitting can be based on misclassification impurity, and it is defined as 1 minus max of P of omega j at node n, and it measures the misclassification error made by a node. The maximum is 1 minus 1 divided by NC, and NC here is number of classes. It is when the records are equally distributed among all the classes, implying the least interesting information. And the minimum is 0 when all the records belong to one class, implying the most interesting information. The next 6 slides show the same example as with Gini index and information gain. Misclassification before split and after split are calculated, and from there you get a reduction in impurity or in misclassification error. Misclassification error with nominal and ordinal attributes. If multi-way split is used, then first you need to have the distinct values from the attribute. For example, marital status have 3 distinct values: married, single, and divorced. And then you follow the same procedure. You get the misclassification error before split and after the split, and then the reduction in misclassification error. If two-way split is used, then you need to try all possible combinations of the distinct values. So with 3 distinct values, we have 3 combinations. Each combination gives you a number for reduction in misclassification error. And from there, you can also say splitting with married and single combined, and divorced is the best among two-way splits. Misclassification error with continuous attributes is similar as with Gini index and information gain. And you will select the split with the highest reduction in impurity or in misclassification error. This figure compares the values of the impurity measures for binary classification problems. P here is the fractions of records that belong to one of the two classes. So you can see all the three measures get the maximum value when P is equal to 0.5 and attain the minimum values when all the records belong to the same class, meaning when P equals 0 or 1. Overfitting is a problem if the tree keeps growing fully until each leaf node corresponds to the lowest impurity, then the tree may overfit the training data. This means that the tree may work well with the training data, but performs worse with unknown data. And there are two approaches to avoid overfitting. One is pre-pruning, meaning stop early. If the split reduces the impurity by less than a preset amount, however, it is difficult to choose the threshold. Another is post-pruning. In this approach, you let the tree grow fully until the leaves have the minimum impurity and then remove branches from the tree. Advantages of decision tree algorithms include inexpensive to construct, extremely fast at classifying unknown records, easy to interpret for small-sized trees, and accuracy is comparable to other classification techniques for many simple datasets.